Section 1.1 Numbers, Variables, and Expressions. Start with a couple of basic ideas. First, we'll define what the natural numbers are and what the whole numbers are. The natural numbers are a set of numbers starting with 1, 2, 3, and continuing on forever. They are what we would also maybe know as the counting numbers. We use 3 periods, or ellipses, to signify that this pattern continues on to infinity. The whole numbers are an extension of the natural numbers, where we also include the number 0. So the whole numbers would be the set containing 0, 1, 2, 3, and again the ellipses to signify that they continue on. So these are the sets of numbers that we will start with, and as we progress in this course, we will learn how to work with other sets of numbers. So now that we have defined the basic numbers that we were working with, we can continue by talking about some special subsets of these numbers, the prime numbers and the composite numbers. A prime number is a natural number greater than 1 that only has 1 and itself as factors. So then we might ask ourselves, is 30 a prime number? Well, by definition it is not, because we can write 30 not only as 1 times 30, but we can also write it as 2 times 15, 3 times 10, and 5 times 6. So it is not prime. If it were prime, the only way that we could write it would be 1 times 30. Is 17 prime? Yes, 17 is prime. I can only write 17 using multiplication as 1 times 17. There is no other way to write 17 using multiplication with natural numbers. So some of the prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, and we can continue going, finding more prime numbers. In fact, it has been proven in mathematics that there is an infinite number of prime numbers. A composite number is any natural number greater than 1 that is not prime. For example, 30 is composite. Right? Since it is greater than 1 and it is not prime, it is composite. Now, all natural numbers can be written using what's called a prime factorization. And to determine a prime factorization, we want to break down a composite number until it is a product of simply prime numbers. So for example, 60 is composite and can be broken down as 2 times 30. Now 2 is prime. 30 is not prime. Can be broken down as 2 times 15. Again, 2 is prime. Is 15 prime? Well, no, it's not. It can be broken down as 3 times 5. Is 3 prime? Yes. Is 5 prime? Yes. So what we've just shown is that 60 can be written as a product of prime numbers as 2 times 2 times 3 times 5. and that is the prime factorization of 60. Now would be a good time to pause and try to find the prime factorization of 224 by yourself. All right, again, I would start by saying, well, I can see that it's even, so it's divisible by 2. And so I can write it as 2 times, let's see, that would be 112. 2 is prime. 112 is not prime. It can be written as 2 times 56. Again, 2 is prime. And is 56 prime? Well, no, it's still even. So let's break it down further as 2 times 28. And again, the 2 is prime. 28 is not. Let's break that down as 2 times 14. And the 14 is 2 times 7. And I think we have our prime factorization. 7 is prime, and all of those 2's are prime. So then 224 can be written as 2 times 2 times 2 times 2 times 2 times 7. So now some definitions of some things that we're going to use in this course. A variable is a symbol used to represent an unknown quantity. An expression is simply a mathematical statement containing numbers, variables, operation symbols, and grouping symbols. An equation is a mathematical statement that two expressions are equal. Now, something that's very important between these two, an expression will never have an equal sign. Right? One of these things. Whereas an equation will always have an equal sign. A formula is a type of equation that expresses a relationship between two or more quantities. One thing that we can do with expressions is evaluate them. So here are some exercises where we are asked to evaluate each expression for x equals 7 and y equals 11. So we have the expression for x. So to evaluate the expression, to find the value of the expression, what we can do is replace the x with the variable, replace the x with the numerical value 7. Now we have 4, and we understand the multiplication, times 7 is 28. So 4x is the same as 28 when x is 7. 3 by x plus 2 we would write as 3 by 7 plus 2. Remembering parentheses indicate some order that we need to follow, so we would simplify within. 7 plus 2 is 9, and then 3 by 9 is 27. Why don't you try this last one on your own? Y by x minus 3 would give 11 by 7 minus 3, which would yield 11 by 4, which is 44. Here we are given some formulas and asked to find the value of the formula for the given value of some other variable. we are given that f is equal to 9z and z equals 12. So like we did in the previous exercise, we would now have f equals 9, and replacing the z with 12, we would have f is equal to 9 times 12, and going through that multiplication, 9 times 12 is 108. So f equals 108. Why don't you try the second one on your own? F would equal 40 over 2 plus 3. We would take care of this division first. F would equal 20 plus 3, as 40 divided by 2 is 20. F would equal 23. One thing that we will need to be able to do in this course and later courses is translate some English words into mathematical statements. Sometimes there are common phrases that we can quickly translate. For example, we understand that the words add, plus, more, sum, and total give us addition, which we use the plus sign for. Similarly, for subtraction, we have subtract, minus, less, difference, and fewer. For multiplication, we have multiply, times, twice, double, triple, and product. And for division, we have divide, divided by, quotient, and split into equal parts. So let's see some examples translating from an English phrase into an algebraic expression. 5 times a number x. Here we would write 5 and immediately next to it the variable x. Remember that multiplication is understood when we have a number directly next to the variable. We understand the multiplication. It does not need to be explicitly written. 6 added to a number can be written as a number, let's just use x, plus 6. A number divided by 10 can be written as x over 10. Remember that the fraction bar represents the operation of division and can be used in the place of the division symbol. 3 less than a number. Here's one we have to be careful about. When we see this less than, we have to remember to switch the order as we see it. So 3 less than a number is written as x minus 3. The sum of two numbers. We don't know what either of the numbers are, so what we would generally write is x plus y, or some other variables. So now let's see an application. Let's write a formula that converts q quarters to p pennies. I often like to use a little table of values to help me write these formulas. So what I might start off with is, I don't want to use the variable there, sorry. Let's just write quarters and pennies. And so let's start with what we know. 1/4 is equivalent to 25 pennies. And similarly, 2/4 is 50 pennies. And 3/4 would be 75 pennies. And what we hopefully notice is that to get the 50, well, isn't that 25 times 2? And the 75 is 25 times 3. And in fact, the 25 is 25 times 1. So now here's where we have to sort of make a little jump. What if we had q quarters? Well, following the pattern, for 1/4 I had 25 times 1, and for 2/4 I had 25 times 2, and for 3/4 I had 25 times 3. So for q quarters, I would have 25 times q pennies. So therefore the number of pennies is given as 25 times the number of quarters.